Tonight we're going to have two relatively short lectures. I wouldn't call them cartoons, but if you want, you can. The first one will be on high velocity flow, and we'll talk a little bit about the so-called Forkheimer equation. There are a couple of classic references given, one by Gertzma and the other by Firuzabadi and Katz, and we'll talk a little bit about that. And then there's a paper by Jones, which is exhaustive in its data, but not so much in its explanation of what they were trying to do with it. They basically painted the page black with data. The simple answer is we use the Forkheimer equation, which is a quadratic variation of, well, I started to say of Darcy's law, but it would be analogous to having a quadratic term in Darcy's law. But of course, Darcy's law is assumed to be a constant gradient, and this will be something that will be parabolic, I guess one could say. So basically the form would be pressure drop is proportional to some constant times velocity plus some constant times velocity squared. This is actually a truncation of Forkheimer's original work, which allowed even higher order terms. Just FYI, something to think about. So what are the applications? The only thing that I could think of in petroleum engineering is really these transient isochronal test, which is multi-step. I should say it's multiple sequences of multi-step or multi-point test, deliverability test on gas wells. And then there's a pseudo-steady state flow, which is sort of a flow after flow test. Again, not really mainstream stuff. There is also another use of this. You don't see it very often, but in the Kappa software suite in particular, they have a rate-dependent skin, and that rate-dependent skin is formulated from the Forkheimer equation. You must have some sort of a variable rate profile in order to calibrate it, which is fine. What you'll notice in the Kappa software is for the drawdown, it acts like a skin, but for the buildup, it actually has a really sharp feature in the derivative. So sometimes whenever you're looking at high rate cases for gas wells, for example, and you end up with a very sharp feature in the pressure buildup, in particular in the derivative, that's usually caused by these non-laminar flow cases. Yeah.
Is that real or is that just a software artifact?
I think it's real. You know, it's a good question. In fact, it's probably too good a question because most of the time I'd say things are artifacts. But this one, whenever you start getting into the tens of millions of cubic feet a day type thing, that's when you start seeing these buildups with these really sharp features. Now, you can also see a buildup with a sharp feature when you have some sort of variable storage caused by gas-liquid interface or caused by casing changes or caused by leaks or other things. Those are harder to match in the software, and generally speaking, they're an artifact matching thing. But what I've noticed, and it is extremely hard to get calibrated on what that coefficient is, the coefficient DSDQ. But once you get calibrated on that, you will match the buildup pretty well. So my answer to you is yes, it's a matching parameter. Cameron, I'm sure you love matching parameters. But physically, at least, it is tied to the concept that there is some Forkheimer-like behavior. Of course, they dumped all the Forkheimer-like behavior in the time-dependent skin term, or in the rate-dependent skin term. Kappa software also allows you to have time-dependent skin, and that is the devil, okay? We talked about the skin factor last night, and we assume that the skin factor is constant. That's C-O-N-S-T-A-N-T, constant. But we know it's not. What Kappa has done by allowing and by making the time-dependent skin factor so easy to use is they've allowed people to use that to make up for errors in the pressure data. Okay, I am personally guilty of maybe 50 steps of time-dependent skin in order to match a poor pressure history. That is illegal. That is not the way to do this. In other words, what I'm saying is I can't get something to work because I have an insufficient history. So I'm essentially creating a variable history in the pressure drop in the side of that to make it match. Very, very illegal, you know. But there are occasions where there's some phenomena going on that you just can't, you can't resolve by constant property means. And you can see it. You know, you'll have a choke change and there'll be a variation, and you can pick that up with a skin. What I'm telling you is from experience, and is way beyond the scope of this course, but what I'm telling you is when you see a choke change in pressure and in rate that aren't, can't be resolved, it's probably an error in the pressure. We assume the rate's correct, and therefore you use a time-dependent skin to fix that error in pressure. And here we go again. I'm going to say this for the 10 millionth time. Take bottom hole pressures. Should solve most of your problems here. How much is a bottom hole pressure gauge, Alex? No idea. How much is it worth to you? Really? I like that. Give me a hug, okay? If a bottom hole pressure gauge for a well that costs $10 million cost $1 million, is anybody going to put it in? No. Well, maybe a Ramco will, but no. Okay. What's the right price? What price do you like? Juan, you're the economics guy. Sorry? 6? Sorry. 6,000 per run. So that's the gauge that you would drop in and leave. That's a memory gauge. That's 6,000 baht or 6,000 US dollars. Okay. So there's a company called Spartec in Canada, and he probably knows this. Their base gauge is about $6,000. And you can drop it through tubing on wireline. It has a special tool, and it will pop in and pop out. But I'm not talking about a memory gauge. Very good. You get a hug. You get star of the day. I'm talking about surface readout bottom hole pressure gauge. How much is it? Give me a number. Not offshore Thailand. Sorry? 200? They'll take that if you'll give it to them. That's not a bad guess, actually. If you were just coming out of the woods, and that's a pretty good guess. Casing conveyed, that is a gauge strapped to the outside of the casing that is cemented in place, and then they fire a perforation. That one started at about 75,000 US dollars. Maybe a little bit more with some of the instrumentation and other surface equipment. So let's say $100,000 just to be even. But how much is a gauge that you would hang alongside? You would run the cable outside the tubing, which is a pain because you have to strap it on every time you make a joint. Actually, that's not a bad guess either. The cost of the cable, the more armor you need, it does go up much more rapidly than I thought. Let me put it that way. If you need a cable that is resistant to chemicals, to environment, to other things, and you're willing to pay for it, it will double the price of the system for sure. But what's a rock bottom number that you'd be willing to pay to put a bottom hole pressure gauge with surface readout? I can tell you that the prices vary from about 40 to 60,000 US dollars. And the variation is really where you are, what the demand is, et cetera, whether they have to put a solar panel and a telemetry system on it, et cetera. But that's not bad. How much is a usual well run? $8 to $10 million. So you lose that. Yeah, that doesn't even show up. So for that little amount of money, we could be resolving things like this, is my point. You'll notice in all my old presentations, I always say, take bottom hole pressures. I know you're tired of hearing me say it, but take bottom hole pressures. But there's so much competition on price right now I think you'll see it come down even more. I really do. But that's a really good intuition, Eric. The cost of the cable was what surprised me. If you're going to go with a base cable, you could probably get a $30,000 unit. But if you're going to go with a heavily armored cable that's resistant to H2S, CO2, other environmental factors, temperature, you're probably looking at doubling it, you know, possibly, because they're going to charge you more to handle it. The cable itself costs more. Yes, sir.
How about the accuracy calculating the multiple pressure from?
So that's probably the question that's confusing most people in the class right now is why not just take the surface pressure and convert it to bottom hole. For dry gas wells, you know, you're usually within maybe 5%. Okay, let's say you can even get down to 2 or 3%. But for cases where you have a lot of gas and a lot of oil and a lot of water, you're going to be way off. I don't know any other way to say, you know, I used colloquial English, sorry. You're going to have substantial error, and it will not be linear. It will vary with the fractions and the conditions in the well. For example, several years ago, I was asked to look at a case where they had measured bottom hole pressure and calculated bottom hole pressure in the Eagle Ford Shale. The measured bottom hole pressure looked like a textbook. The calculated bottom hole pressure looked like something that a child would have drawn with with a crayon. It just made no sense at all. It was by far the worst case I've ever seen. But the point was, it's a very volatile system, and the behavior of the gas bubbles coming up just completely obliterated the calculation. If you want me to tell you that it's close enough that surface-derived pressures converted to bottom hole are close enough, I will say that, but I have to say there's a caveat. For production analysis, I'm okay with that. But for pressure transient analysis, I think you're going to find serious issues. When you shut in the well and those gas bubbles start rising up, you're going to get a hell of a lot of fluid movement in the well bore. The calculations, no matter how complicated they are, they're not going to pick it up. For $30,000, okay, let's be generous. Let's say $50,000. You never have to worry about that again. You know, do you guys pay insurance on your car? You know, that sort of thing. Sure, you do. That's the way you have to look at these kind of things. It's almost like a safety investment. If somebody told you that, you know, your compliance cost for a facility, that you're building a facility and you have to have twice as many safety valves in it because that's a decision your company's made, even if that cost $250,000 more, you're going to do it. Because what's the implication of a safety failure? Think about it. I know maybe it doesn't make so much sense in all the world's calamities, especially like today, but there's a cost, a huge cost, and especially, you know, if anybody gets hurt or dies. So the first thing we talked about a moment ago was the Gertzma approach, and unfortunately Gertzma plotted this sideways, if I can say that. He plotted porosity on the y-axis, and he plotted this so-called beta coefficient on the x-axis, and he has some sort of a coefficient here. And he came up with a line. And admittedly, there's not a lot of character to this line. There's a lot of variation. What would be the purpose of having a relationship that correlated some factor for high velocity flow with porosity? Again, we haven't talked about this yet, but again, we're talking about something that's even more complicated than permeability. We have talked about permeability versus porosity correlations throughout this course. Now we're talking about a variable that is even more complicated than permeability. It actually has the units of inverse length. So that's what beta is. It is a parameter in an equation. It is an empirical-ish parameter, but it has the units of reciprocal length, 1 over L. So what they tried to do was correlate it with porosity, and then that way they wouldn't have to go to permeability to do it. Along comes Feruzabadi and Katz, and they start talking about all the different language used for high velocity flow. Now, Fancher, Lewis, and Barnes, I believe I have you reading that, correct? Anybody read that yet? No? That's a long report from 1933. And then you start seeing a whole bunch of these other relationships. Anything with tech, cats at all, they're all working together, and so on. So tech. And then finally Gertzma comes along, and they named it the coefficient of inertial resistance. And again, it's a parameter to represent Forkheimer's equation, or as they call it, the deviation from Darcy's law. In order to explain this, Firuzabadi and Katz show what is typically thought to be Poiseuille type flow, which is a parabolic velocity profile, and then they show what the shape of a fluid particle or a fluid element, would look like. So it'll be elongated here, where there's high velocity. As it slows down, it compresses. As it slows down even more, it actually compresses even more, and then it begins to speed up, and then it stretches out again. Well, to explain this, at low velocity, we have the typical onion of streamlines. So all the streamlines are clearly shown. They follow the curves of the pore, etc. At higher velocities, you can see the streamlines are starting to break apart. They're starting to get sharper, and in the center, that is. And then there's an intermediate where along the edge, you begin to have a breakdown. You no longer have film type flow over here. You have a breakdown, you have eddies forming, and so forth. But the center still has this Poiseuille or Darcy type flow. And then later on, there's just nothing but eddies. So at a high enough of velocity, and that would be the case where no matter what pressure gradient you cause or what pressure drop you cause, you cannot achieve any higher rate. So that would be the maximum. Again, these are just cartoons to sort of explain that. So Firuzabadi and Katz took some additional data. They took studies of other people or data from other people, and then they are now plotting this coefficient on the y-axis, and they're plotting permeability on the x. They have a bunch of data down here for unconsolidated samples. I would argue that unconsolidated samples are going to be pretty hard to measure the permeability. For one thing, it's probably going to be even harder to measure the beta parameter. You notice that the permeability is up here. This is 10 Darcy's. This is 100 Darcy's, and so on. So these are very, very unconsolidated sediments. Then they have what they call their consolidated curve, and just to explain again, there's a lot of deviation here. You could just as easily pull that line down a factor of 2 or more, and it would still be just as good of a fit, if you want to call it that. Then they change and look at a set of limestone data, so the same parameters, the beta factor, and now they're multiplying permeability times porosity, but this time it's for a limestone sample, and you can see again that the data are reasonably well represented by that straight line. Again, they're just trying to come up with another relationship. These are all of the relationships that were present at the time when Jones wrote his paper, and you'll notice that he has correlations that are based solely on permeability. There are others that are based on permeability and porosity, and then there are variations of that from the literature. You can see Gertzma's equation, and then Katz et al. And so forth. And again, the goal of this work is to try to have a predictive relationship for beta. Why does anybody care about beta? Why is beta important? What are you going to use beta for? Why all this effort to correlate it? Beta is your high velocity flow coefficient. You're going to have to use it in modeling. You're going to have to use it in simulation. So rather than you run an experiment, they've given you these relationships in the hopes that they may be reasonable for those kinds of calculations. You could, of course, run your own experiments. How would you determine the beta factor? Nobody knows at this moment because you haven't read ahead in the notes, right? Okay, so we'll talk about that. Alex, if it's the Forkheimer equation, for Darcy's law, we plot essentially the pressure drop versus the rate, and we get some sort of a trend. That's not going to work here because this is a squared term. So how would you take, if you had, hopefully this doesn't screw up, but if you had a relationship that's delta P is equal to AQ plus BQ squared, how would you make the equation of a straight line? How about this? Would that work? Okay. So in essence, that's the kind of thing that we're going to do in a moment. It's not exactly clear as the same approach. What they do instead is they use Darcy's law and they plot that on the left-hand side, and then the right-hand side is linearized. We'll show you that in just a moment. Okay, and one of the last plots is by, again, by Jones. He's showing a heavy amount of data here. Let's quickly reproduce his so-called line. We'll draw our own. Red on red's kind of risky. Anybody in here ever work for Schlumberger? No? You do want to work for Schlumberger? Why not? Remember, you're being recorded. Speak into the microphone. You're not good enough? I've heard a lot of things in this class. I've never really heard that before. Sorry? Oh, okay. So when are you going to tell me the truth? When it stopped recording? Okay. So these are log cycles, and so if you were making confidence limits, you would have at least one log cycle of variation, probably a little bit more, right? So your calculation of the beta factor is probably off by a factor of 10. Or sorry, it could be off by as much as a factor of 10. Now the reason I asked you that a minute ago, Alex, if we use that equation that I just drew for you, and we estimate the beta factor from field performance data, okay, everybody take a deep breath, close your eyes. Everything we've talked about so far is for core, okay? But Huppert came along and he said, let's use the same concept. Let's use delta P over Q and estimate behavior for field performance, right? So now you're estimating the beta factor for field performance from this particular expression, okay? Do you think the beta factor you calculate from field performance and the beta factor you calculate from core are going to be close? Let's take a quiz. I don't have even one maybe. Maybe. Okay. Explain the maybe. Okay. Now, have a candy or a piece of pizza or something and don't say anything. Let's see what they say. Why is it not going to happen? Perfect. Does everybody hear him? Different scales. The core scale is like this. The reservoir scale, the minimum size would be the size of this building. That's what, like 1,000,000,000,000 to 1? Or something crazy like that? I actually had a project, I'm not making this up, where the company came to us because they had gone to someone else, and the someone else told them that they could estimate betas from field performance data. And they were consistently estimating 10,000 times different. And they could not understand why. And you just explained it. Now, a factor of 10,000 is pretty damn big. But conceptually, I don't think the same forces are at play when you're changing scales by, a factor of 1,000,000,000,000 or something. Okay, let's very quickly go through this derivation. This is Forkheimer's equation for flow in porous media. Tonight, when you go to sleep, print out a copy of this, put it under your pillow. I guarantee you'll fall right asleep. Okay, so it's the gradient dP dx is equal to the viscosity divided by the permeability. This is the actual permeability. Velocity plus some constant c plus our beta factor, which is units of 1 over L, multiplied by density multiplied by velocity squared. C is a units conversion constant. There are 1.01325 times 10 to the 6 dynes per centimeter squared times 12 inches per foot times 2.54 centimeters per inch. Okay, that's what that conversion factor is. Beta is the inertial flow coefficient. It is in feet reciprocal. How do you like that for a unit? Mr. Lowe, is that a good unit? Eric, you like reciprocal feet? How do you make a reciprocal foot? I can't even think of that. Okay, but that's the dimension. That's what we chose. So the first thing we have to do is we have to say that the velocity is equal to the reservoir flow rate divided by the cross-sectional area. That's obvious enough. The definition of reservoir flow rate is the standard flow rate multiplied by the formation volume factor, and again divided by the cross-sectional area. No problem there. We substitute all these in. We now have the gradient. We now have mu b. We now have k over a. We now have QSC. We got a whole bunch of more frustrating things. We have that units constant. We have the beta coefficient. We have density. We have the formation volume factor squared, and we have area squared. What's going to happen here, and of course we have rate squared, is we're going to now substitute the definition of density, and once we do that, we're going to cancel a few things. We're going to go on ahead, we'll have a viscosity multiplied by the formation volume factor gas. Again, we're going to reach out, we'll have this extra term here, then we'll have formation volume factor gas, and everything's pretty much more or less the same. Now we're going to divide through by mu g bg, so we have 1 over mu g bg, the gradient, 1 over Ka, the rate, constant, mu g, area squared, rho GSC, rate squared. Okay, now we have to say, okay, we're going to multiply through both sides by some reference. It could be the initial, but for right now, we'll just say it's the reference. And when we do that, we're going to have this term, no problem. This term, no problem. We're trying to make it look like a liquid, if that helps. And then these terms. We separate, that is, we move all these out. We have the dx term here, and we bring that over here. When we integrate this, what is this going to be, class? That's a pseudopressure. Okay, so in the next page, we go on ahead and substitute in, and that gives us the same thing that we had before, which is a pseudopressure type function. You do some algebraic manipulation, and you have pseudopressure expression on the left-hand side, and then you have all these other terms which are constant, integrating 0 to L dx. This is, we're going to go ahead and divide by L, and then we end up with this, no problem. We end up with this, no problem. What's going to happen next, class? We now divide through by mu I bi over A QSC. A mu I bi QSC, pseudopressure difference L. What is that known as, class? Well, if you remember Darcy's law, this is the expression, and what we'll do is we'll solve for this permeability product, or quotient rather, and this is going to be defined as that whole term. Okay, so all of this is defined as 1 over K dl. So that's from Darcy's law. That's the permeability that you would calculate from the experiment. So we now have 1 over the permeability that you would calculate uncorrected from the experiment. We have 1 over the correct permeability, and then we have all these other terms. The only thing that isn't constant in this mess is viscosity. Viscosity is not constant. So how do we represent viscosity? We assume that viscosity is taken at some average pressure, so we do assume it's a constant. And then when we take data in the laboratory and we calculate the Darcy's law of permeability, we take the reciprocal, we plot it versus rate, we get a trend like this. So what this tells you is there's a rate-dependent permeability concept, and the absolute true permeability is here at this intercept at rate equals 0. So there's a laboratory methodology for estimating the beta factor and the equivalent liquid permeability. How does this work in the laboratory? Has anybody ever done these experiments? You would have to take multiple experiments. You'd have to calculate KDL using the permeability approach we talked about before, using the steady state approach, and it'll of course be wrong because of high velocity flow, and you take it at different rates. Well, the machine is programmed to do this automatically. So it will take several different sampling rates and several different pressures, and it will report the data like this. And then it will also provide an equivalent absolute permeability from that. So if you have a sample that you're going to ask the laboratory to calculate beta, this is what's going to look like. They're going to create some sort of a plot like this. And the machine, like I said, it's programmed, it runs automatically. The parameters that you want are beta and the true permeability. Okay. All right, in the interest of clarity, I'm